The next speaker is Marcelo Losada in a work with Sebastián Fortín and Federico Holick, the dynamical approach to logic structure of quantum systems.
In this talk, in this presentation, I'm going to talk about the logical structure of classical properties, the logical structure of quantum properties, and the transition between these two kinds of logical structures when we consider a classical limit process as a system which is under a classical limit process. Well, the organization of the talk is the following. First, I'm going to talk about classical systems, classical properties, and the logical structure of classical properties. Then I'm going to talk about quantum systems, quantum properties, and the logical structure of the whole set of quantum properties. After that, I'm going to talk about the classical limit from a logical point of view. If we have a quantum system which undergoes a process in which it becomes classical or semi-classical, we can describe this transition from the logical structure of properties, and we can describe the transition of the logic. Then I'm going to talk about the different dynamics we can consider and why unitary evolutions do not allow this kind of transition between the two kinds of logical structures, and we need to consider other kind, non-unitary, or other evolution. Then I'm going to mention some conclusions. Well, as you know, in classical mechanics, a physical system can be represented using a phase space. There we have an example, the phase space of a single particle, which is the set of all pairs of momentum and positions. Well, in classical mechanics, pure states are represented by points in the phase space. Here we have the state of a single particle, which is a pair of a position and a momentum. And well, properties are also represented using the phase space, are represented by subset of the phase space. Here, for example, we have an example. If we consider, again, the single particle, and we consider the property A, which is the particle has momentum p sub 0. This is represented by the subset we have there, which is a constant line of momentum equal to p sub 0. And well, we say that a system has a property A if the point we represent its states belong to the subset of R sub A. Well, now we can consider the set of all classical properties, and we can see that it has a logical structure. Well, first we can represent a logical consequence using an order relation given by the inclusion. So if we have two properties A and B represented by the subset R sub B and R sub A, we say that the property A implies the property B if the subset R sub A is included in R sub B. Also, we can represent the conjunction between two properties using the infimum, which is given by the intersection of two sets. So here we have the properties, and the intersection of the properties A and B is this intersection. Then we can represent the disjunction between two properties A and B by the supremum, which is given by the union of the two sets. And then we can represent the negation of a property A by defining an orthocomplementation, which is given by the complement of sets. So considering all this structure, we have a logical structure. So the all properties has a logical structure. When we can also study or the distributivity of this lattice of this logic, and we can see that it's a distributive logic. So that means that properties satisfy the distributive equality, which is given there. So it is easy to see this. Here we have a property A represented by a subset R sub A, and a property B represented by a subset R sub B. And here we have one member of the equation, the equality, and well, we can compute that, and it's easy to see. Here we have the set represented A. Here we have the disjunction between B and the complement, and finally we have to do the conjunction between this. This is the whole phase space and the set R sub B, and we obtain R sub A. Then we can compute the other side of the equality. Here we have the conjunction between A and B, which is the intersection. Here we have the intersection between A and not B. Then we have to compute the union, and we obtain the same set, the R sub A. So we can see that the set of all classical properties has a logical structure, and also is a distributive lattice, so it is called a Boolean logic. Well, now I'm going to talk about quantum mechanics. In quantum mechanics, physical system is represented using a Hilbert space. Pure states are represented by normalized vectors of the Hilbert space. And properties are also represented using the Hilbert space, are represented by closed subspaces of the Hilbert space or by their corresponding orthogonal projectors. Here we have some examples of properties, representation of properties. Well, we say that a system has a property with certainty if the vector representing the state belongs to the subspace that represents the property. That is similar to what we have in classical mechanics. Well, we can also consider the set of all quantum properties, and we can see that it has a logical structure also, but well, it has a logical structure as well as classical property, but it's a different structure. Now we can see that. We can define a logical consequence between two properties using the order relation given by declaration. That's similar to the classical case. Then we can define a conjunction between two properties using the infimum of the lattice, and which is given by the intersection. This is again similar to the classical case. And well, we can also define represent the disjunction between two properties. We use the supremum, but here we have the first difference. The supremum is given by the sum of subspaces, because the union of subspaces is not a subspace. And well, here we have the difference. And well, we can also define represent the negation of a property, defining an orthocomplementation, and which is given by the orthocomplement of subspace. Here we have the second difference. We don't use the complement of set, we use the orthogonal complement. So the set of all properties, of all quantum properties, has a logical structure, but it's different to the classical logic. And we can see that the main difference is the non-distributive of this logic. So here we have 4 vectors. We have A, B, and the orthogonal we can think that this vector represents subspaces. So here we have the subspace A and the orthocomplement of A, denotated by minus A, and B, and then the orthogonal complement of B, which is minus B. So we can compute both sides. Here we have, it's very easy to do this. We have to remember that here we have the union, but here we have the sum. So we have two subspaces, and the sum is the plane. And then we have to do the intersection between these two subspaces, and we obtain the subspace A. Well, we can also do the computation of the other side. Here we have the intersection of two subspaces, and we obtain the null subspace, or that means the subspace that we only contain the zero vector, and we can also do the disjunction, and well, we obtain the null subspace. So here we obtain not a distributive equality, but a distributive inequality. Well, that's the reason why this logical structure, the logical structure of quantum properties, is not Boolean. It's not a distributive logic. Well, this main difference is related with non-commutativity. It is proved that non-distributivity of properties is related with the non-commutativity of their corresponding projectors. So if we have a sublattice of properties which are non-distributive, their corresponding projectors are non-commutative, and if we have some projectors that are non-commutative, their corresponding sublattice is non-distributive. Well, up to now, I have talked about the logical structure of classical properties and the logical structure of quantum properties, and now the idea is to try to describe a classical limit process, in which, well, a physical process in which a system, a quantum system, goes from a quantum behavior to a classical behavior. So if a quantum system undergoes a physical process such that it becomes classical or semi-classical perhaps, then we should expect that its logical structure should also undergo a similar process, a process from or a transition from a quantum logic to a classical logic. So that means going from a non-Boolean logic to a Boolean one, or in terms of commutativity, going from non-commutative projectors to commutative ones. Well, if we try to do that using the Schrödinger picture, we have a problem, because in Schrödinger picture, observables do not evolve, projectors do not evolve, so logical structure of properties do not evolve. So we propose to study or to describe this using the Heisenberg picture, in which observables evolves and also the logical structure evolves. Well, here I'm going to consider a standard unitary evolution in the Heisenberg representation. We have two observables, O1 and O2. There is the commutator, which I call C. And if we suppose that this observables evolves in a unitary way, we can easily obtain that the commutator also evolves in a unitary way. So if two observables do not commute at the beginning, they will not commute at the end. And if two observables commute at the beginning, they will commute at the end and all times. So this kind of evolutions do not allow to go to describe the transition from a quantum logic structure of properties to a classical structure, a classical logical structure of properties. Well, we can try to describe this transition allowing other kind of evolution. For example, if we consider a non-unitary evolution, here we have the commutator, and here we have the expression of the commutator. And since it's not unitary, we can express this in the other way, in the way of the previous slide. So here we have C, and we can see that if two observables do not commute at the beginning, they can commute at the end. It depends on the evolutions. And well, if two observables commute at the beginning, maybe they do not commute at the end. Also, we have the inverse process of a classical limit here. We start with a classical structure, and then we obtain something which is not classical. So, well, it is possible to go from a quantum logic to a classical logic if we consider this more general evolution. Well, also we can consider other options. For example, a quantum channel. Here we have a general quantum channel represented by Kraft representation. Well, here is the evolution of the state, so we have to use this in terms of the Heisenberg picture and consider how is the evolution of the observables. And then with that, we can block this problem. We can obtain such kind of transition. Well, here is a very easy example. It's a toy model example it's not a realistic model, but it's only to show the general idea of this approach. Here we have a Hamiltonian, two-level Hamiltonian with a real eigenstate and eigenvalue and an imaginary eigenvalue. Here we have an observable, and we can see that at the beginning they do not commute. Then we consider the time evolution operator given by this, and well, we can obtain the Hamiltonian on different times, and also the evolution of the observable, and we can also compute the commutator, and we obtain this expression. So at the end, we have a limit that this commute. So from a logical point of view, at the beginning, the projectors of their spectral decomposition generates a non-Boolean logic, and at the end, at the infinite, the projector of their spectral decomposition generates a Boolean logic. Well, here there are some conclusions. We talk about the main difference between classical and quantum logic. We also connected this with the existence of not commuting projectors. We also suggested that if a quantum system undergoes a physical process such that it becomes classical, then its logical structure should undergo a transition from a quantum logic to a classical one. Then we showed that unitary evolution do not allow this kind of transition, and that other kind of evolution, like non-unitary, could allow this kind of transitions. Well, that's all.
Thank you. That's very interesting. Can you just tell me something more about the sort of process you're imagining? Like, what kind of process is it where something starts out a quantum object and coming on?
What kind of process are you imagining? What kind of process would happen if something starts out a quantum object and becomes classical?
Well,
And can it go the other way? Can something start out classical and become quantum?
classical go quantum, I'm not sure. It's only something that mathematical could be. But the other way, from quantum to classical, we were thinking on the coherence process in which we can obtain we can diagonalize the state. So if we use that kind, we consider that kind of evolution, but in the Heisenberg representation, we expect to obtain a transition from the quantum logic to a classical one when we are in that research.
Yeah, one example is Brownian motion, for example. But I mean, this is what is done in theoretical physics, but the hard work is to show that, let's say, the Heisenberg, if you use Heisenberg equation, forget about logic, I think this has nothing to do with logic, it has to do with showing that Heisenberg equation for suitable choice of a state, because the classical limit has to do with states, converge to a classical evolution. That's what most of the work done in derivation of a classical limit is along these lines. But for people that are using Heisenberg equation, but you can do also the same using states. Sometimes Heisenberg equations are useful, for instance, Brownian motion, to get Brownian motion from a complete quantum description of an heavy particle in a gas, and then you, in a suitable limit, you can get, this is done by many groups in mathematical physics, shown rigorously how you get from that in very some simplified model to the classical equation. So there are plenty of examples.
Okay.
I was going to ask his question, but since he asked it, maybe I'll just make a suggestion or a comment, right? So again, you actually never said the word time when you have with the T in there, right? And I thought perhaps you were leaving open the door that this didn't even need to be time as a parameter. There could be other parameters that you want to scale to do this. And of course, what comes to my mind, right, this looks very much like the Wigner-Inonu contraction, which is one way you can go from one algebra, say one Lie algebra to another Lie algebra by taking a limit. The two most famous examples are how you go from Poincaré to the Galilean algebra in the relativistic limit, or how you go from you go from a sphere to Euclidean plane by taking the radius of the sphere large, right? So one could imagine other, you know, you kept saying a unitary evolution, but you weren't saying unitary time evolution. Well, it could be there's some other scale that's changing.
Yeah. Okay.
Well,
Yeah.
do you want to say something?
Oh, no. Okay.
No, my question or suggestion is that perhaps it's interesting to study what are the features that the effective Hamiltonian has to have to obtain this kind of evolution for a classical limit. I mean, I would like that two things that commute, that do not commute, begin to commute, and okay, in a closed system within an evolution, a unitary evolution, you cannot find that, but perhaps there are interesting conclusions if you study effective Hamiltonians to see what happens. Something.
But excuse me, Olympia, if it is a Hamiltonian, it will lead to a unitary evolution, isn't it?
No, but non-self-adjoint.
Ah, okay. Well, it's a
Yeah.
special
something, yeah.
Hamiltonian. Okay.
Special Hamiltonian.
There is another option. In cosmology, the Hamiltonian.
Time-dependent Hamiltonian, perhaps.
Yes, typically the Hamiltonians that the people use to these things are non-Hermitian Hamiltonians, but there is another option. For example, in cosmology, the Hamiltonian is proportional to the scale factor that increase with the expansion of the universe. So in this case, the Hamiltonian change with time, so it's not exactly the
Linear way.
yes. And in this case, you can study the it's not non-unitary, but yes, it's not unitary, but
you allow
it's-
for
it's-
complex eigenvalues, so you got this exponential factors.
yes. You can study that. There is a work of Kiefer and Polarski that in which in where they study the commutator between the position and momentum, and they show that when the time tends to infinite, the commutator goes to zero. Some people call this decoherence without decoherence.